Hi. Some say that transfer learning is the next driver for the machine learning success. But what we are actually transferring in transfer learning? Most of you would probably say the features, isn't it? Well, let's find out. The agenda for today is as follows. First, I will give a bit of introduction for those of you who are not familiar with transfer learning. I will explain what's the challenge in healthcare industry. I will present what kind of experiments designed in order to find out whether transfer learning is beneficial in our case or not. I present the results and practical conclusions. Before we start though, my name is Michał, and my background is computer science. Over the years, I've been working on many R&D projects, mainly related to parallel computing, high-performance computing, and bioinformatics. And for more than 3 years now, I've been working on various projects related to deep learning. Right. So, what is transfer learning? Transfer learning can be defined as the improvement of learning in a new task through the transfer of knowledge from a related task that has already been learned. In other words, we don't have to train our deep learning model from scratch. We can take one of the models that were pre-trained on a very large, publicly available dataset and hopefully reuse some or even most of the features in our own settings where we don't have that much data. The benefits of transfer learning are well known. We can train our model in a shorter time using less data. Moreover, our model may end up with higher accuracy, and this kind of models also tend to generalize better. So this all sounds really great, isn't it? As a result, transfer learning, mainly or in particular from natural images, has become a de facto standard in medical imaging. However, we also know that transfer learning will work best if the features that were useful to solve problem A are also useful or are also generic enough to be useful to solve problem B. And here we've come to the main challenge in healthcare. When we look at natural images and compare them to healthcare images, we immediately see they have not much in common. As a result, features that are useful for natural images may not be that useful for our healthcare images, which are much more specific. Therefore, the question is, can we benefit from models that were pre-trained on natural images to improve the performance of our healthcare models? Right. In order to find out, we've designed a few experiments. Before we start though, we need to first select a task. So what task are we going to solve? So quite frankly, we went for the most straightforward image classification for several reasons. First of all, it's relatively easy to find public dataset to evaluate this problem. And the more datasets we have, the better we can generalize. Moreover, I also strongly believe we are not focusing just on image classification here, because exactly the same convolutional networks can also be used for object detection or in basically many other computer vision tasks. So with tasks selected, let's talk a little bit about experiments now. So first of all, we are interested in what's the impact of network initialization on the model performance. So we'll be comparing the same networks trained on the same data sets, just initialized either randomly or with pre-trained weights. In the second experiment, we would like to see whether the pre-trained weights can actually be reused as they are or not. We'll be trying to achieve that, but freezing selected parts of the pre-trained network and fine-tuning the others just to see whether the features from those frozen layers can be directly reused, and what's the impact on the model performance. One note here is that whenever I mention pre-trained weights, I actually refer to the ImageNet weights, which is de facto a standard in computer vision now. Right, so we selected a couple of convolutional networks. These are networks that are basically proven to work well on the ImageNet dataset. As you can see, we've got two large models and two relatively small models with respect to the number of parameters. And in addition, we designed also a small custom CNN just to see whether a small network can also compete with the large networks that were really designed for tough problems. And here's the architecture of the small of our small network. Basically, we've got it's very simple. We've got basically 4 blocks, each consisting of convolution, ReLU, batch norm, and max pool, which is all followed by global average pooling and 2 dense layers for classification. So very straightforward architecture. Right, probably the most important part, data sets. So for our experiments, we've selected 3 medical data sets. The first one consists of images of small patches of images that are used for histopathologic cancer detection. And this is basically a binary classification problem. Either have cancer or not. And as you can see, both classes are pretty well represented, so the problem is actually balanced, I would say. The second data set consists of retina images. So this is type of images that is used for diagnosing diabetic retinopathy, which is actually the root cause of blindness. It's extremely small data set. It's got less than 4,000 images. These are very large images, and they are spread across 5 classes in an imbalanced way. And the third data set, these are images. These are microscope images coming from the Human Protein Atlas. And this is also a fairly small data set with less than 15,000 images. They are spread across 17 imbalanced classes. Additionally, we also wanted to, for sanity check, we also wanted to have one data set with natural images, and we went for the very famous cats versus dogs data set. This is, of course, a toy data set in our case. However, we wanted to have one with natural images just to see how things would work if we played with natural images. So in total, 4 data sets with different number of classes, images, and resolutions. And some of the data sets are more balanced than the others. For each data set, each data set was divided into trained, validation, and test subset with the stratified option. And importantly, in order to account for class imbalance, our default metric will be area under the ROC curve. A bit about training regime. We applied some pretty standard image preprocessing and augmentation techniques, and we wanted to keep it simple. We didn't pay that much attention to hyperparametric tuning, in the sense that we primarily wanted to see what's the impact of transfer learning, rather than spending. We didn't want to spend like weeks on tuning hyperparameters for each specific data set, because our data sets are rather, I would say, tough, and we basically wanted, first of all, to see what's the impact of transfer learning. So that's why we went for pretty standard hyperparameters. We used categorical cross-entropy as loss function, Adam optimizer, and all the configurations were trained for 53 epochs. Actually, the only hyperparameter that was tuned was the learning rate. So we wanted the learning. So we basically wanted each data set has a correct learning rate, not too small or not too large, but just right for the network to optimize steadily. Additionally, I think it's worth mentioning here that in case we use the pre-trained networks, for the first 3 epochs, we only trained the dense layers responsible for classification with relatively higher learning rate, and only afterwards, so starting from epoch 4, we trained the rest of the layers, the rest of the pre-trained layers with the default learning rate. Otherwise, when the network was trained from scratch, we used the default learning rate from the very beginning. So this is a pretty standard approach in transfer learning. But I think, anyway, it's worth mentioning. As for the technology stack, we coded everything in TensorFlow 2.0 and Python. The computations were run on our high-performance computing platform.
Podejdziesz do mnie?
Come again?
Sprawdź na
So all the computations took 4 days using 16 V100 GPUs. So just for you to imagine, that would take roughly 2 months on a single V100 GPU. So it's quite a lot of computations. Right. So we've come now to the interesting part, results. And at first, we would like to compare 2 settings. Same networks, trained in the same way with the same hyperparameters on the same datasets, just with different initialization, random or pre-trained weights pre-trained on ImageNet. So here you can see quite a lot of aggregated results. So maybe let's focus first on the upper left chart for a while. So the blue and the orange lines here represent the training and validation performance for the pre-trained networks. And in a similar way, the green and red lines here represent training and validation performance for the same networks, just trained with random initialization. Yes? So what we can see here, the first observation is that the pre-trained networks tend to train much faster for each dataset. The second observation can be, if you compare the validation curves, we can see that that the pre-trained networks tend to reach higher level on the validation dataset than for those networks that were trained from scratch. What else? We can also see that the pre-trained networks are much more stable in the sense that the confidence interval between individual runs, the confidence interval marked here as gray area, this confidence interval is much lower, or the variance, in other words, is much lower for those networks that were pre-trained. So the training in this case is much more stable or predictable. And last but not least, I think, if you look at the performance of this small custom designed CNN, we can also see that it performs just as well, if not better, than the large networks that are trained from scratch. Right. I was also tempted to quantify the speedup that we can get from the pre-trained network. And by speedup I mean how much faster in terms of epochs, a pre-trained network can achieve at least the same level of validation performance as the same network just trained from scratch. And depending on dataset, we achieved speedup between 4 and 10x, which is quite a nice result, I would say. If you look at the cats versus dogs dataset, this is a very different dataset, as you know.
it's with natural images, and we can see much higher speed up here. However, it stands to reason because the ImageNet was trained on this kind of images. Yeah, but anyway, even for our healthcare images, we are still getting quite nice benefits. Right. Let's have a look for a while on a test set. So this is the inference phase, run on the best checkpoint, saved throughout the whole training process. So for the cancer and retina datasets, we can see we've got around 5% of improvement from the pre-trained networks. Yes. However, this doesn't have to always be the case. For instance, for the protein dataset, sometimes we cannot clearly distinguish whether it's better to train from scratch or from ImageNet weights. Things look obviously very different for cats versus dogs dataset, where we are getting quite a lot of improvement by using the pre-trained net. Interestingly, when we again look at the small CNN, we can see that it performs more or less the same as the large networks that were trained from scratch. Right, so we've learned that initializing network with pre-trained nets can improve the performance of our training, even in healthcare settings. So now we've been interested in how much of this improvement comes from the actual feature reuse. So we've designed an experiment in which we are freezing selected portions of the layers just to see whether those fixed features can be directly reused and what's the impact on the model performance. So what we can see here is we can see here validation curves for the cancer dataset. And first of all, it's plain to see that regardless of the network type, the best performance can only be achieved if we fine-tune all the layers. Yes. Interestingly, even if we freeze like 10% of the layers that are closest to the network input, we immediately see quite a large decrease in the model performance. So that actually suggests that even the most basic features, or those features that were meant to be most generic ones, cannot be directly reused in our healthcare settings. To some extent, this can also be visualized by running t-SNE on the pan-ultimate layer of our network. And again here we can see, so these charts were generated for the cancer test set running on Inception v3. And we can again see here that even if you fine-tune 90% of the layers and freeze just 10%, our clusters are not that clear, meaning that the features that are produced by the network are not that useful to distinguish between cancer versus non-cancer images. And only if we fine-tune basically the entire network, we can clearly see like much better clusters, let's say. Just to mention, the results for the other healthcare data sets are basically very similar. So the conclusions are basically the same, and things are looking very different for the cats versus dogs dataset, where regardless of the numbers of frozen layers, the network was extremely good at distinguishing between cats versus dogs. And if we visualize this, we can again see that even if we freeze all the layers in the network, the model is actually perfect in distinguishing between these two classes. Right. So on one hand, we've learned that initializing the network with pre-trained weights can greatly improve our model, even in healthcare settings. On the other hand, we've learned that even the most basic features cannot be reused as they are. So what's the matter? Well, it turns out that even if you destroy all the ImageNet features and simply inherit the scaling of the weights, we can get a pretty good convergence speed. So in these charts, we can see the validation performance depending on the train step. So the blue line here represents the training from scratch, from random initialization. The orange line represents the same, but the network was initialized with ImageNet weights. And importantly, the green line here represents the training where all the ImageNet features were destroyed, only the scaling was preserved. The mean and variance of the scaling for each filter. And we can clearly see that using only the scaling of the pre-trained weights can actually improve the convergence speed of the network. Right, and here we've come to conclusions. So the main takeaways for you. First of all, initializing a network with pre-trained weights can greatly improve the speed of training. And on average, on our medical data sets, we saw the improvement on the level of 7x. Secondly, ImageNet initialized networks almost always achieved higher performance on test set. And again, on our medical data set, the average improvement was over 4%, which is a non-negligible number if your metric is already above 0.9. And third, the ImageNet features may not be that reusable or may not be that generic as we previously thought, but are extremely good starting point for your training. So you basically need to fine-tune the entire network, but statistically this is an extremely good initialization or starting point for the neural network. And last but not least, small customly designed convolution networks can also achieve very good results on healthcare datasets. So in our experiments, the network that we designed, the small network, it performed just as well as the large networks that were trained from scratch. That may also suggest that the large networks that were designed specifically for the ImageNet are simply over-parameterized for the problem. And as a main takeaway, I would recommend that you use transfer learning in your projects, because it actually is the next driver of machine learning commercial success. Thank you.
Thank you very much. Do you have any questions?
Yeah, thank you for the talk. I have a question about actually freezing the very first layer, so the ones very close to the input. What was the original size of images? Actually, I'm very curious about the ratio of pixels, whether actually the ratio influenced the very basic features. So if you scale to a square and the original picture was not a square, how much this kind of change influence the result?
It's a very interesting question, thank you. Especially in medicine, where some small, like even pixel-wise elements can influence the result. Yeah. So we went for the vanilla architectures, Inception, ResNet, and we've been scaling down actually the images to the default resolution of the network. And for the cancer data set, the pictures were pretty small, like 96 by 96, and we haven't been doing any upscaling. Yeah, the global average pooling did the job. So we've been actually like scaling down the images, all the images to the default resolution of the network. So we actually did not look at what's the impact of this on the change of the features.
Okay, thank you. And have you actually have any rectangle images in your dataset? Or all of them were square, simply bigger or smaller?
Let me get back.
Because usually
datasets.
the pre-trained architectures have square as the input, if I remember correctly.
Yes, so the protein dataset was square, retina like almost square. This is not the original like ratio. Yeah, it was changed for the presentation just. And cancer was square. Interestingly, cats versus dogs is not square.
Okay, thank you. Actually, I have a second question. May I? Okay. Have you tried with different number than 3 epochs before actually changing the learning rate? This is due to the very first slides of your presentation.
To be honest, no. For some time we've been starting to train the network without freezing the pre-trained layers and just start to train the entire network from the very beginning. This worked as well, however the convergence speed was not that fast because we were at the beginning destroying a little bit the pre-trained features, which is not really good. I think in some papers they recommend to freeze the pre-trained layers for 5 epochs, but it's a rule of thumb, so we went for 3. Thank you.
Great. So thank you very much for the presentation. It was super interesting. And my question is, do you actually are actually some institutions or hospitals that are using the stuff that you are creating? I mean, are there doctors that actually utilize these kind of tools?
Not exactly this research, but what surprised me that I've read a couple of papers on transfer learning in healthcare, and yes, what surprised me is they, in most of the cases, they actually use the ImageNet pre-trained weights. So that was one of the reasons I wanted. These are natural images and these are like medical images, so it doesn't fit very well. So that was one of the reasons I actually wanted to see what's going on here. So we are not directly using this anywhere because this was an R&D project just finished 2 weeks ago. But I hope we will be using this knowledge somewhere in the future.
Hi, thanks very much for the talk. It's really interesting. I'm just wondering whether you thought it would be useful to have kind of like a medical specific image data set, so like medical net instead of ImageNet.
Yeah, of course, it's always better if if the data set from on which you are pre-training is similar to your case. Yeah. The problem is that the medical data sets are not that open as natural images. And I think that's one of the reasons why currently the ImageNet is so popular even in healthcare. If we had a model that is pre-trained or more domain-specific images, that would be great. But we don't have that kind of pre-trained model now.
Thank you.
Thank you very much, Michał, for your speech.